So the next section we're going through is 11.4, which is the comparison test. So far we only know a very select group of series, what their convergence and divergence criteria are. So we've got this integral test, which is very time consuming and may not work for a lot of things. We have p-series and we have geometric series, but now if we change it in any slight form, we aren't 100% sure what's going to happen. So we want to be able to find a way to compare these two types of series we know nice criteria about, the p-series and geometric series, and we want to compare what we have to those that have the nice criteria to be able to determine if they're going to converge or diverge. So for example, if we look at the series, which is a sum of 1 over 3 to the n plus 6, if you were to just ignore this plus 6 in the bottom, it's going to look very similar to a geometric series. So that would be the sum of 1 over 3 to the n, which you can rewrite if you want to in the form ar to the n minus 1. So this would be a geometric series. The value of a is 1/3. The value of r is also 1/3. And that would be convergent since the modulus of r is going to be less than 1. So because of this, our series is very similar. Adding that plus 6 in the bottom shouldn't do a whole lot of change to it. It really just makes that denominator even smaller when n is larger. So intuitively, we should be able to see that our series converges, but how can we actually say it? So we want to compare our terms to this one we know is convergent. So every single term in our series is going to be positive, and one comparison we can make is that when we add this plus 6 to 3 to the n, we can make this inequality here. So 3 to the n plus 6 is definitely greater than n for all n greater than or equal to 1. So when you flip those fractions, you can reverse the inequality sign, and the terms in the series we're given are smaller than the terms in that geometric series that's convergent. So every single term in our series is smaller than this geometric series. And the geometric series sums to a over 1 minus r. So 1/3 over 1 minus 1/3, which simples down to a half. So what we can actually do is look at those partial sums. So if we take the nth partial sum, that would be when you sum up from 1 to n of our terms. Every single one of these terms is smaller than 1 over 3 to the n. So we can say for this finite sum, the partial sum is smaller than the partial sums of the convergent geometric series. And because each of those terms is positive, this is going to be at most 1/2. So it follows that every single term or every single partial sum you look at is going to be somewhere between 0 and 1/2. And the more terms you add, the more that thing's going to increase, but it's going to be bounded above by 1/2. So it tells us our sequence of partial sums forms a bounded increasing sequence, and we can apply a theorem called the monotone convergence theorem, which gives us that our series actually converges. So this idea is really just the comparison test. You're going to have two series. So we have one series, an, which has general term an, another one which has general term bn. They have to have positive terms, so you need that criteria to happen. So what the first part tells us, if we know bn is convergent, and you're able to make this inequality that an is less than bn. So when you go ahead and you sum up bn and sum up an, the series of summing up an is smaller than bn. But since the sum of bn is going to be finite, it's going to force this smaller term to also sum up to something finite. The reverse is true if you can show that bn is less than an and bn is divergent, When you sum this up, it'll be something infinite, which will force the series that's bigger to also be infinite. So AN would be a divergent series. So you're going to want to make a comparison with what you're given to a p-series or to a geometric series, because they have the really nice criteria based on the common ratio and based on the power. You know immediately whether it's convergent or not. And so you need this inequality to be true. Showing the inequality is the most difficult part. So we're going to have another test very soon that I'm going to recommend you use more, because you guys don't tend to like using the inequality, but you don't want to throw this method out because it sometimes will be the only method you can use. But you just need it to eventually be true. The first couple terms don't satisfy it, that's fine. It just needs to eventually be true. So you've got two things that you have to show. The first is the series you have and the series you're comparing it to both have to have positive terms. And then you have to make one of these two inequalities. Then you're able to say that both series converge or both series diverge. Okay. So let's go ahead and look at an example. We're going to look at the sum of n divided by 2n to the third plus 1. So the best thing you can do is you've got to make a guess first. Ignore all the constants that are in front of it. Just look at n over n cubed. So it's going to look like a p-series. So if you ignore those constants, you get n over n cubed, which simplifies down to 1 over n squared. So that's a p-series. The value of p is 2. So we're going to expect that ours is convergent because this p-series is convergent as well. So we need to show that our terms are smaller than the terms of the ones that converges. You could try to show it to this one, but I'm going to recommend trying to prove the inequality to this unsimplified version. That's going to be better for you and easier to show it. So we want to now apply the comparison test. First thing we have to do is we have to show everything's positive. So if we look at our original series, you know that n is definitely greater than 0 for all n greater than or equal to 1. You know the denominator, 2n cubed plus 1, is also greater than 0 for all n greater than or equal to 1. So if you go ahead and look at the ratio of these two, this is definitely positive for all n greater than or equal to 1. And the same is true about the other series. You can use the n cubed, you can use the n squared for this one, doesn't matter. N squared is greater than 0 for all n greater than or equal to 1. So the reciprocal is also positive. Okay, so this shows both of our series have positive terms. Now, since I know the thing I'm comparing it to is convergent, I want to show our terms are smaller. So the second part of this we want to show is we want to make a comparison between our terms and these other terms. So first we're going to look at the bottom. If you look at 2n cubed plus 1 and n cubed, well, 2n cubed is definitely bigger than n cubed. So this is true for all n greater than or equal to 1. So when you flip it, 1 over 2n cubed plus 1 is less than 1 over n cubed for all n greater than or equal to 1. Now we need to have an n up top, so this is why comparing it to just 1 over n squared is a problem. You want to take this inequality and you want to multiply both sides by n. So you get n over 2n cubed plus 1 is less than n over n cubed, which that one simplifies to 1 over n squared. And this is true for all n greater than or equal to 1. So the terms in our series are smaller than the terms in the p series that's convergent. So what we can say is, since this is a convergent p series, by the comparison test, our series is convergent as well. Okay. So I'm going to show you why you shouldn't do the comparison with this simplified version to start with. It's really natural to want to do that, but you run into a bit of a problem. So I can't just immediately state that happens because sometimes it's not going to be true. It might seem like it is, but no, you've got to actually show some justification for it. So if I had made a comparison between our terms and the simplified version, you could definitely do that first step. 2n cubed plus 1 is greater than n squared, so that's not a problem. So when you flip it, you get an okay inequality, but now you need an n in the numerator up here, but I can't just put an n because I don't have that up here as well. I can't do that simplified. I can't multiply one side by n and say that this inequality still holds true. It's a variable. N could be 3, 4, 5, 6, 7. You need it to be true for all values of n. So this is a problematic step. It's not true. You can't multiply but one side and not the other, which is why you want to go ahead and make the comparison with the unsimplified version you started with. This tells you whether it's convergent or not, but this is the one you want to use to make the comparison with these inequalities, okay? So let's get some more practice. Let's look at something that is a geometric series. So if we look at that, we want to make a guess again. So the guess we want to make is, I'm going to ignore the bounds for right now. You're going to just ignore any constants. So that -1 doesn't do a whole lot. So this would be 6 over 5 to the n. So this is a geometric series. And the value of r is equal to 6 over 5. So it's divergent. Okay. So that -1 in the bottom shouldn't do a whole lot. I'm going to expect that our series is divergent as well. So because it's divergent, we want to show our terms are bigger than these terms, which are divergent too. So first thing we've got to do is we're applying the comparison test. We need to show that everything has positive terms. So first, 6 to the n is definitely positive. The denominator, 5 to the n minus 1, is also positive. And these are true for n greater than or equal to 1. So if you look at the fraction, the ratio of these two, that's definitely greater than 0 for all n greater than or equal to 1. Same thing holds true for the series we're comparing it to. So we've already got 6 to the n is greater than 0, 5 to the n is also greater than 0. So the second series, 6 to the n over 5 to the n, is definitely positive for all n greater than or equal to 1. So the terms in both the series are positive, so we can go ahead and now make the comparison between the two. So if we look at 5 to the n minus 1 and 5 to the n, the inequality sign is going to go towards 5 to the n, so this is true for all n greater than or equal to 1. So when you flip them, you get the reverse inequality, and that's true for all n greater than or equal to 1. Now you can multiply by 6 to the n. So you get 6 to the n over 5 to the n minus 1. It's greater than or equal to 6 to the n over 5 to the n. for all n greater than or equal to 1. Okay? So the terms in our series are bigger than the terms in the geometric series that's divergent. So what we're able to say, now erase it and give you a little bit nicer of a view. Since 6 to the n over 5 to the n, the sum of that is geometric. The value of r is bigger than 1. It's divergent. We can say by the comparison test, our series also diverges. So let's take a look at a couple more examples. Let's determine whether the series is convergent or divergent. So we've got the sum of n squared over n cubed minus 1. So the first thing we want to do is we want to figure out our guess. So if we ignore this minus 1, it's going to look like n squared over n cubed. So our guess is it looks like the harmonic series, which we know is divergent. So because of that, we're going to assume that this series is as well, but we've got to go through the comparison test to show it. So first thing we have to do is everything has to have positive terms. And so one thing you'll notice is we're starting at 2 in both of these because if you plug in 1 for the original series, it doesn't actually work. So we need to first show that everything is positive. So we've got n squared. That's definitely greater than 0. And in this case, it only has to hold true for n greater than or equal to 2. Then the denominator, n cubed minus 1, is definitely greater than 0 for all n greater than or equal to 2. So when you look at the ratio of these two, n squared over n cubed minus 1 is also positive. And this is true for all n greater than or equal to 2. And then same thing, just 1 over n. That's clearly going to be positive for all n greater than or equal to 2. So both of these series have positive terms. So the next thing we need to do is we're comparing this to something that's divergent. Our terms better be bigger. So when you sum up the smaller terms, it still blows up, which means the bigger terms also have to blow up. So we need to look at a comparison between these two. So n cubed minus 1 is, again, I'm going to use this unsimplified version for the comparison. This is less than or equal to n cubed for all n greater than or equal to 2. So when you take the reciprocal, our denominator in a fraction becomes greater than 1 over n cubed for all n greater than or equal to 2. So now we want to take this and we want an n squared in the top, so we can multiply by n squared since it's going to be positive. So we get n squared over n cubed minus 1 is greater than or equal to n squared over n cubed, which simplifies so that our terms are bigger than the terms of the harmonic series for all n greater than or equal to 2. Okay? So since the harmonic series diverges, our terms are bigger, we get its divergent as well. I'm going to clean this up, give you a little bit nicer of a visual for it. But since the harmonic series is divergent, by the comparison test, our series has to be divergent as well, because the sums, our terms, are bigger than the terms of the harmonic series. So when this sums up to something infinite, this has to sum up to something infinite. Well, this is infinite, so this can't be. Same thing happens for both of them. Right? So let's do one more example. Let's determine if the series is convergent or divergent. Right. So this one's a little bit harder to make a guess as to what's going to happen. But again, sine squared is always going to be stuck between -1 and 1. So ignore that plus 1. So our guess will be it looks like n over n cubed, which is a p-series. So for our guess, since sine squared of n is less than or equal to 1, this looks like the sum of n over n cubed, which is the sum of 1 over n squared, which is a convergent p-series. Since p equals 2, which is bigger than 1. Okay? So now we can go ahead and we can actually apply the comparison test. All right. So we need to make sure that everything is positive. So n is greater than 0. Sine squared of n is positive because it's sine squared. And then 1 plus n cubed is also positive for all n greater than or equal to 1. So you've got a bunch of positive terms when you take their division and multiplication. N sine squared of n over 1 plus n cubed is definitely greater than 0 for all n greater than or equal to 1. And then in terms of the one we're comparing it to, that's definitely positive for all n greater than or equal to 1. Okay. So now we want to make our comparison. We think this is convergent, so we better be able to show that our terms are smaller than the terms of the convergent series. Right. So if we look at the denominators between each of these, and we want to use that unsimplified version, 1 plus n cubed is bigger than n cubed. And this is true for all n greater than or equal to 1. Okay? So when you take the reciprocal, you get the reverse inequality holds true for all n greater than or equal to 1. So now you go ahead and you multiply both sides by n, and you get n over 1 plus n cubed is less than n over n cubed, which is exactly the 1 over n squared. So this holds true for all n greater than or equal to 1. Now you've got that sine squared of n, but really, since sine squared is less than 1, sine squared of n over 1 plus n cubed is less than or equal to n times 1. Okay. So you're able to make this because sine squared of n is less than 1. So this is true since sine squared of n is less than 1. Okay. So this holds true for all n greater than or equal to 1. So basically, the terms in R series are going to be smaller than the terms in the P series. So since the sum of 1 over n squared is a convergent P series, by the comparison test, the series which we're started with, it's a sum from n equals 2 to infinity of n sine squared of n over 1 plus n cubed is also convergent. Okay. All right. So this test is nice, but it can be quite tedious, and making that inequality tends to prove troublesome for a lot of people. So we have another test that's similar, but the criteria is a little more relaxed and probably something you're more familiar with. So maybe we still can compare it to geometric or p-series, but you can't prove this inequality. It might be the opposite of what you want. We have a different test we can use in that case. So let's look at the series, which is 1 over n to the 6 minus 1. Same thing again, if you ignore this minus 1, you get 1 over n to the 6. That's a convergent p-series since the value of p is 6, which is bigger than 1. If we wanted to use the comparison test on this, we would need to show that our series is smaller than 1 over n to the 6. So this way, we sum up something finite, our terms are smaller, it also sums up to finite. However, we actually get the opposite. Since n to the 6 minus 1 is less than n to the 6, when you flip the fractions, you get the reverse inequality of what you actually want. So this is a problem. It's the exact opposite of what we need. So when this happens, you're going to want to use something called the limit comparison test. And I'd recommend using this to begin with because you guys are much better at taking limits. And that's exactly what you're going to do. You make the same comparison you would before, but now you're going to take a limit of these two things. And that's all you need to show. So what it actually tells us, if you have two series that both have positive terms, and the limit of their ratio is some constant, c, that is positive. So this is a key thing. This is one of the hypotheses. This limit has to go to something that is greater than 0. If it goes to 0, you can't use this test. If it goes to infinity, you can't use this test. But if this limit is something positive, then you can say both series converge or both series diverge. And if you know what you're comparing it to is convergent or divergent, you get what happens to your series for free as well. So there's a short little proof that I'll show you. You know this thing is going to something positive in its limit. So there's going to exist a small value m that's below it and a big value m that's above it. Because this limit goes to c, that term is going to be close to it for large values of n. So basically you can say when n is super large, it's going to be trapped between these two values. So what you get is this nice inequality. You get m times the terms bn is less than an, and then you get that constant times bn as well. So basically, if you know bn is convergent, we can apply the first comparison test we learned. So bn is convergent, so this thing is finite, which means our terms in the series are finite. By the comparison test, this has to be convergent as well. In the case that you know bn is divergent, when you multiply it by a constant, it's divergent as well. So an has values that are bigger than m times bn. This is divergent, so an has to be divergent as well. So it all follows directly from the actual comparison test, but now you just have to take a limit and it has to go to something positive. So we're going to be given some series an. We got to find that comparison, and then you want to take a limit. So let's go ahead and start with an example. We've got the sum from n equals 3 to infinity of n plus 2 divided by n plus 1 to the third. So we do the same thing to make the comparison, just ignore any of those constants that are in there. Don't care about this one, don't care about that plus 2. So our guess is it's going to look like the sum of n over n cubed, which is the sum of 1 over n squared. Okay? And that one's going to be a convergent p-series, since p equals 2. So we'd imagine that our series is going to be convergent as well. So what we want to do is apply the limit comparison test. So you've still got to show that both of these terms are positive. So AN, doesn't matter which one you call AN and BN, makes no difference. You've got the n plus 2 over n plus 1 cubed. That's definitely greater than 0 for all n greater than or equal to 3. And we're going to let Bn be the one we're comparing it to. In this case, you don't have to use that simplified version because you're just going to take a limit. It's going to be the same thing. So we're going to compare it to 1 over n squared, which definitely is greater than 0 for all n greater than or equal to 3. So what we want to do is we want to take the limit as n approaches infinity of an divided by bn. So remember, when you're dividing by a fraction, it's the same thing as multiplying by a reciprocal. So you have an, which is n plus 2 over n plus 1 cubed. You're dividing it by bn, which is the same thing as multiplying it by its reciprocal. Okay? So this is equal to the limit as n goes to infinity of n cubed plus 2n squared over n plus 1 to the third. So you could absolutely go through simplifying it, but it's a polynomial. This thing goes to those ratio of the coefficients. It goes to 1, which is greater than 0. So this is a key. You have to make sure that you state that because it's part of the hypotheses. Okay? If you did want to see, let me erase some of this so you can see a better, clear shot of it. So you take an divided by bn. Here's an, the reciprocal of bn. So when you simplify it out, you get the same thing. If you want to show this in the normal method, you divide by that highest power. So you multiply top and bottom by 1 over n cubed. Simplifies very nicely. And then from that, you still get the same limit. So this thing goes to 1, which is positive. So you have to state this because it's part of the hypotheses. If you don't, you're not satisfying all that criteria. So we've got all these tests. Each of them have different hypotheses. Probably a good idea to keep a running list of what you need to show for each of them. But now, since this limit goes to a positive number, what it means is these two are really proportional to each other. They're growing at the same rate or decreasing at the same rate. So if one is convergent, the other is convergent. So since 1 over n squared is a p-series, with p being 2, which is greater than 1, it's convergent. And so now we can say by the limit comparison test, ours is convergent as well. So I'm going to assume that most of you are probably going to end up doing this. We learn that comparison test because sometimes this limit comparison does fail. And when that fails, that's when you kind of want to go back and see if you can show this inequality. But I would recommend starting with a limit comparison before you do a comparison test. Right? So let's try one more example. We've got the series, which is 1 plus 4 to the n over 1 plus 3 to the n. So same thing as before. Let's see what we compare it to. Ignore these plus 1s. Looks like 4 to the n over 3 to the n. So our guess is this looks like the geometric series which is the sum of 3 to the n over 4 to the n. Backwards. 4 to the n over 3 to the n. Okay. And so that would have a common ratio of 4/3. We're going to assume that this thing's divergent. but I'm going to apply that limit comparison test. And you could see why the comparison test isn't going to be as well, because you have a lot going on in the numerator and denominator. That inequality is going to be hard to show. So first, we've got our term an, which I'm going to make this series given to us. It's 1 plus 4 to the n over 1 plus 3 to the n. That thing is definitely positive for all n greater than or equal to 1. Our second term is bn, which is 4 to the n over 3 to the n. Again, this thing is clearly positive for all n greater than or equal to 1. So we want to go ahead and we want to take the limit as n approaches infinity of an divided by bn. So this is the limit as n approaches infinity of 1 plus 4 to the n over 1 plus 3 to the n. And you want to go ahead and divide this by bn. So it's the same thing as multiplying by the reciprocal. Okay. So now we're going to go ahead and group the like pieces. We've got 1 plus 4 to the n divided by 4 to the n. And then in another fraction, I'm going to group the stuff involving 3 to the n. Okay. So this first fraction simplifies a lot nicer. 1 over 4 to the n is 1 over 4 to the n. 4 to the n over 4 to the n is 1. Okay. For this second piece, I can't simplify it as easily because we've got that addition in the denominator. So I'm going to go ahead and I'm going to divide all of the components by that 3 to the n. So this is the limit as n approaches infinity of 1 over 4 to the n plus 1, because we can see what's happening there. Then the top 3 to the n over 3 to the n is 1. In the bottom, you get 1 over 3 to the n plus 1. So now you can see a little bit nicer. This is going to go to 0. This is going to go to 0. So this limit will equal 0 plus 1 times 1 over 0 plus 1. So in the limit, the ratio of these two goes to 1, which is greater than 0. So this means they're behaving and growing or decreasing at a similar rate. So since the sum of 4 to the n over 3 to the n is a geometric series, with r equaling 4/3. So in absolute value, this is bigger than 1. It diverges. So the series we started with grows at a similar rate to this divergent series. So we can say by the limit comparison test, so the series we're given, sum from n equals 1 to infinity of 4 to the n over 1 plus 3 to the n, also diverges. Okay. So this test is going to be pretty much used when you are given something that looks like a geometric or a p-series. So our main goal with all of these is, given this thing, is it going to be convergent? Is it going to be divergent? And when you look at it, if you can immediately tell it looks geometric or p-series, apply one of the comparison tests. Start with limit comparison, and if that fails, which basically means that you're going to get the limit equals 0 or infinity, then you're going to want to go back and try the comparison test instead.